Hello and welcome to the sixth session of our playlist where we are trying to learn about agentic workflows using LangGraph. So in this session we'll be talking about incorporating human in the loop in our graphs, and following is the session structure that we'll be following. And guys, I want to tell you that human in the loop is a pretty big topic. There are multiple methods, multiple techniques over here, so I'm dividing the entire module of human in the loop into multiple videos to make the playlist more modular and for you guys to easily follow. So in this session we'll be talking about this particular section, approval section of these three popular techniques of incorporating human in the loop. Alright, so let's start. So first of all, let's talk about the intuition behind human in the loop. Why do we need human in the loop? The graphs are working pretty fine already. So first of all, when we are talking of incorporating a generative AI application and in the form of an agentic workflow in a production environment, in a critical industry, for example healthcare industry, for example pharma industry, or wherever where basically the response has to be absolutely validated one, we can't go wrong with the response in those cases. Okay, so we need to have some kind of accountability of the workflow. We need to have some kind of consistency in the responses. We need to have some kind of reliability in the responses that are generated by our agentic workflows. So what better than human to provide all these things, right? So what we are trying to do with human in the loop is we are combining our agent, our graph basically, with some sort of human feedback in the form of various steps, in the form of various intermediate steps rather, to add accountability, consistency, and encourage control over the agent, as we know that providing full autonomy to an agentic workflow is not the right way to go across when we are dealing with some critical data, or when we are expecting some critical responses from our workflow. So adding human in the loop comes in various shapes and sizes. Here I've listed 3 techniques of adding human in the loop. First one is human modified states, or I should rather start with approval because that is what we will be covering in this particular section. So first one is approval. What we are targeting with approval is we will try to interrupt the execution of our graph and make it wait for human approval to go with the further execution steps. So what we're trying to do is we're trying to incorporate a step in which a human has to provide approval. A human will basically monitor or look at the output, the intermediate output generated by the graph. If he feels that okay, everything is going fine, he will provide an approval and the graph will continue to execute. And if the human feels like this is not going in the right direction, then he can simply rerun the graph, or he can stop the working of the graph. A second kind of technique of incorporating human in the loop is time travel. Sounds fancy, right? What is time travel? Time traveling is basically when we are trying to incorporate a step in which a human will basically be able to reverse the steps of the graph and re-execute it as per his demand. So what we will be doing is, for example, we have 3 nodes. Say that we have 3 nodes, node 1, node 2, node 3. Okay, we are going from node 1 to 2, 2 to 3, and for example we reached node 3 and a human validated this output and he felt like okay, this is not the right output, or this is not the right direction where we want to take this output from. So what he will do is he can generate a feedback that will cause the graph to re-execute from node 1 with a new input or without any new input. That depends on the human. So what we will be doing is, we are time traveling. We are basically re-executing. We are going back in time, changing a few things, and then re-executing as per the human demands. So this is time travel. We will be covering it in future sessions. Then there is human modified states. We know that an agentic workflow in LangGraph is basically a state machine, and a state is modified by each of the predefined nodes using the node functions. A node can be an LLM, a node can be a tool, a node can be any arbitrary function that we wish to define. But using this particular technique, we can modify the steps manually. We can modify the states manually by inputting some particular state. So for example, if we want to alter the state or alter the input, alter the response in an intermediate step manually, we can do that. So that's also one method of adding human in the loop. Okay. So in this session, we'll be talking about the approval technique in detail. But guys, before starting with the in detail steps of how to incorporate this, we will have to actually revisit and understand a few concepts around some functionalities of LangGraph that are critical to understanding human in the loop, because this becomes a little bit advanced concept in LangGraph. So you need to understand a few more things, and these concepts will benefit you when we develop a full-fledged agentic workflow in the future. All right, so we'll be starting with this particular concepts. I have listed down each of them. So we'll be learning about streaming graphs. How can we stream graphs? What is graph streaming? We will revisit the memory structure, the checkpoint, thread, all those concepts, and we will try to add something on top of that so that we can understand the working of these particular techniques. And we will be revisiting the add messages reducer. Yes, the same reducer that has been performing a lot of heavy lifting for us. And I will introduce you one extra functionality that the add messages reducer provides us, and how it helps us incorporate human in the loop in a cleaner and easier manner. After that, once we have built the base, we will take a look at how can we incorporate human in the loop. I have abbreviated it as HITL, through interruption or approval. It is also called as interruption. It is also called as a breakpoint. All right, cool. So let's jump into the code and talk about graph streaming. My bad. So here I have created a separate notebook where I am trying to explain graph streaming and some basic functionalities that will help us understand the working of human in the loop workflows. All right, so first of all, starting with streaming states with graph.stream. You might be remembering that up till now, we have been executing a graph and consuming its output using the graph.invoke method, right? We are invoking the graph as if it's also a runnable, and we are consuming its output. But you can easily understand that our requirement while incorporating human in the loop is something different, because what we are trying to access over here in human in the loop is we are trying to access some intermediate states, some intermediate steps, and work on top of that. So for example, again considering the same example, I would rather go in a separate area. Okay, so usually our workflows look like this. Okay, I would rather go with nothing, and stroke style normal. Okay, so normally what happens is, say that we have an initial state or the start, and then we go boom boom, then we go to and say assistant node, okay, and then we go to some tools and stuffs like that, some other nodes, say just name it node, okay, and then after that we go to the end, that is the final state, or I would rather call it end, and this is the start. All right, so what was happening up until now is when we were using graph.invoke input and thread configuration, it used to look something like that, right? Yeah, cool. What this was providing us is it was providing us a kind of an interface where we were inputting the initial state or the user query that we want to start with. If it is a memory enabled one, we were basically including the conversation history along with the user query, and that was executing this particular graph.invoke method was executing this entire graph and providing us a final state. So it was providing us a, I would make it a dotted one and I would place it here, okay, and it was providing us a final state. Brother, this is going all over the place, right? Cool. Final state. So this is what was happening up until now using the graph.invoke method. But now our requirements have changed. Now what we're trying to do is we are trying to look into these intermediate states and try to include something manually, trying to include ourselves. We are humans, right? I don't know if some alien is watching this video, but considering that you guys are humans, we're trying to include ourselves in the form of an intermediate step between these nodes somewhere here. So for example, if the assistant node releases or it basically creates a particular state called as S1, what I'm trying to do is I'm trying to look at this S1 and tell it, in case of approval, I'm trying to tell it, looking at this S1, I feel like, okay, this S1 is not good enough, man. I don't want to execute with this S1 response, this S1 state. Go back or cut the response over here. And if I feel like, okay, if I get the output of S1 and I feel like, okay, this S1 looks good enough, please proceed. Please proceed to this node. Then the entire graph will get executed and everything will happen as expected. So what we're trying to do is we're trying to consume the intermediate states of this graph, which is not possible through graph.invoke. For that, we need to introduce something called as graph.stream. This also has a similar kind of syntax or input parameters as graph.invoke, but a few things are different, so we'll talk about them. First different thing is we have to provide a stream mode to this graph.stream process, okay? So this particular S1 step or the intermediate state observation and human interference can be achieved through graph.stream, okay? Let's see. So graph.stream enables streaming responses from the graph, allowing for continuous data flow. This is particularly useful for longer outputs or when you want real-time updates. So remember one thing, graph.stream is actually faster, and it also has async supporting. It also supports async abilities. That is, when you're trying to develop an app out of this particular agentic workflow, you would want to use async functions. You would want to incorporate it with the async ability so that it can handle multiple requests and everything goes according to the plan. It basically doesn't choke out in a particular step, and block the entire application from working. If you want to learn more about async functions and all, you can check them out. But yeah, just remember that this provides the async functionalities as well. And whenever you will be trying to deploy a graph with agentic workflows, you will be using graph.stream. And you would not want to use graph.invoke. We use graph.invoke usually for testing development purposes. Okay. So one use case of using graph.stream is it is beneficial when the response is lengthy or when you want to handle the output incrementally. Example in chatbots, real-time applications, or for interactive experiences. This is what we are looking forward to. We are trying to interact with the graph as it executes, to interrupt its flow whenever we want to. And one good functionality that graph.stream provides, which I have not mentioned over here, is you can observe the execution of the graph step by step at a very high level of granularity. I mean, you can also see the graph being executed at this level, that you can also see each token being generated by the LLM while the execution of the graph. So it provides a very high level of granularity, and it also provides you a method to handle the output incrementally, node by node, state by state. Okay. One important use case for developing with graph.stream is when you want to interact with the graph at a granular level, as I mentioned, like node level or even token level, and want to insert operations which is particularly required to add HITL features to our graph. So this is what we are concerned with. We are trying to interact with the graph at a granular level, right now at a node level, but we can also interact at the token level, which I don't know why you would want to do that. Maybe for testing purposes or to trying to understand how the response is being generated, but that's a very good transparency to have in our application. Okay. If you want to take a look at this token level thing, you can mention it in the comments. I'll create a small clip for that, maybe a YouTube short, maybe, I don't know. Okay. Now let's look into it. So this is the summarizer graph which we created in the last session, and I have actually executed and created this graph once again, and you can see how it looks like. Start to conversation. Conversation is basically the assistant, and then it summarizes the conversation based on a conditional edge, and if it doesn't see it fit, I mean if the length of the messages is less than 6, it does not summarize it, and it goes directly to the end. We talked about this in detail in the last video. Good. Now, streaming graph has two kinds of methods, .stream and .astream. So we can use .stream, and we can also use .astream. So .astream is the async version, and .stream is the sync version of this particular method. Async method, as I said, when you will be wanting to deploy this as an endpoint, you want to apply this particular code in API and kind of an architecture, front end, dealing with the API, back end, all those things. When you deploy it as an application, you would always want to use the async methods, but right now we are good with sync methods. We are just learning about the development right now. And then there are the mode settings that I just wrote here. Stream mode, this is an extra input parameter that we need to provide while working with graph.stream. So there are two popular modes. One is the updates and one is the values. I have downloaded, or I have stolen this particular picture from this particular link. You can check this out. So what is the difference between mode, updates and values? Okay, say that in node 1 the output state was message A, and in node 2 the output state or maybe let me explain it in this way. Okay, let me just go over here and again create something like I get confused with these diagrams all the time, man. Initial state, and then we have, say, 1, and then 2, and then 3. Cool. And then we are going to the final state. All right. So say that our initial state over here is something like, or we should just start from node 1. So say that when the initial state entered node 1, the node 1, we know that every single node updates the state. Say that the initial state was A, okay, and then as it went to node 1, it updated the state by adding B to it. Okay, or to make it and get it in sync, let's say that we actually had nothing over here as an initial state, and it went, when it crossed through node 1, node 1 updated the state from nothing to A. So this is the output of node 1, and then again it went to node 2, and node 2 again updated the state to A comma B. It added another element to this, and then it went to node 3, and node 3 again updated the state, and this particular state we received as the final state. So if we are using let me just select all of this. I need more space actually. Shoot. Cool. Taking it far from the busy world. Okay, so now if we are using the particular mode, say updates, let me just write mode updates. Okay, and then placing it here. Good. And then there is the other mode called as values. All right, so if we use the mode updates, the updates mode will provide us output in the form of the update made to the state as the graph gets executed. So when it passes through 1, it will provide us A, because this is the update that has been made, right? And then again when it passes through 2, it will give us the value B. It won't provide us A comma B. Why? Because, let me just get it on all and blue. Cool. Why? Because the update which was made by node 2 is just B, although the updated state is A comma B. But when we select the stream mode as updates, it just provides us the update made to each state as the output. And then again when it tells us about node 3, it just provides us the value C, because that is the update which is being made to the node, to the state. Now when we talk of mode values, it provides us the entire state at each particular node, or I should say, if you remember about my memory session, at each particular checkpoint. All right, so at node 1 it will provide us node 1's output A, because that is the entire state over here. But in node 2's output, or in this checkpoint, or in this state modification, it will provide us the updated state, the entire updated state, not just the updated part. And then it will provide us the entire updated state as we pass through node 3, which is A, B, C. So this is the concept of the different stream modes, updates and values. Another thing we'll see here. So this is what they were trying to tell you. Node 1 messages A, and then node 2 messages B, node 3 messages C. But when we consider the stream mode as values, it will provide us the entire state as it updates, and not just the updated part. Cool. You can check out this particular link over here. Why is my internet so slow, man? Literally. Yeah, you can see all of that, the image which I stole, and everything. You can read about all of this to know about more about streaming, because it is very important. Streaming is actually pretty important. Now, let's see it work. So first of all, we will be exploring the streaming in LangGraph, and we will be exploring the updates mode. So this is how you take output out of a stream. We take output, as I said, step by step as the states get updated in the agentic workflow or in the graph. So we need to provide a for loop over here. For chunk in graph.stream, this is the initial state, the input. This is the config, which is the thread configuration. And then this is the stream mode. So currently I have selected updates as the stream mode, which means I'll only receive the updates which are being made to the state at each checkpoint. Okay, printing it. So right now this is how the output looks like for each of the chunk. Let's observe it. Boom. My bad. Let me just select all of this. Okay, shoot, man, I don't know how to select this thing. Yeah, cool. And let's now maybe open something, a notepad maybe. A notepad. Okay, let's add something else. Yeah, so this is how the output looks like. Let me zoom in a bit. So first of all, it is a big dictionary, like quite a big dictionary, which has this particular key conversation, and then inside that conversation key we have the messages part, the first message that I asked it, the response rather of the first message that I asked it. So this is basically the update that is being made to the state, because the initial state is the question that I asked it, which is hi fiddler here, and the output which I got, or the state update which has been made, is this AI message. So this is what it provided me alongside a lot of metadata. Cool. Also, I have written here, notice the difference in output formats in different stream modes. You can easily observe that this entire updated state which it is providing me has been enclosed inside this particular key called conversation. Now let us see how it looks like. Basically, I've just tried to print it in a proper format for this particular message. So you can see it only provided me the update which is being made to the state. AI message, hello again, fiddler, how can I help you today? Which is the AI message response. Now let's try observing the output from the values mode, asking it the same question, hi fiddler here, config stream mode. Now remember this, I am continuing this conversation in the same thread configuration, so it will create three. Basically it has the length of messages, or the length of the states over here is 3, because we already had 2 messages over here. First one is the hi fiddler here, which I asked it, and then the AI message which I received, and on top of that I'm again querying it, hi fiddler here, now with the stream mode values. So this is how the output looks like. So if I try to print it in a better way, I am again querying it, again I'm querying it. So you can see that now when I'm printing it using the stream mode values, it is providing me the entire state, the entire updated state, and not just the updated part. So first I asked it hi fiddler here, then it replied me, hi fiddler, it seems like you're eager to chat. Then again I asked it hi fiddler here, hi fiddler here, hi. I mean, it's providing me the entire state. And if you're wondering why it is occurring so many times, even though I asked it only once, because we are working in the same thread configuration, so it is storing the entire conversation history over here. When you execute this code yourself, you'll get to understand it properly. So now let's explore a few more important stuff about checkpoints and threads. So basically, let's go down to the session structure. Yeah, this one. So we have completed the intuition and the streaming graphs part. Now we are revisiting the memory structure to take a look of what memory looks like and what other things do we need to know to apply human in the loop. Revisiting the checkpoint. As you know, a checkpoint represents the current state of a conversation or interaction at a specific point in time. It captures essential elements such as blah blah blah. I've not mentioned that. You can easily see that it basically captures essential metadata like what is the next node and other informations, like there is also a checkpoint ID, stuff like that. Messages is the all exchange messages, context, configuration. So these are the things, metadata. These are the things basically which are stored inside a checkpoint. Basically, it stores the state and alongside that some metadata about that state. Now, yeah, let's look at this. So first of all, revisiting these topics. A thread, the conversation occurs within a memory thread that tracks all interactions in a structured manner. It is basically the collection of checkpoints. Checkpoints is as the conversation progresses, every significant change, every state update creates a new checkpoint, results in the creation of a checkpoint. Each checkpoint represents the current super state of the conversation. Why are we calling this super state? Because it is the updated version of the previous state. So every checkpoint is created whenever the state gets updated. So every checkpoint is a super state of the previous state. Okay. This image will make everything clear. And state snapshot. So as we know that when working with LangChain, our messages are stored in AI message objects or system message objects or human message objects. In the same way, the checkpoints are stored in this particular class called as state snapshot. So it is just a data structure in which the checkpoints are stored, encapsulates all the necessary info about the states leading up to that checkpoint alongside important metadata. Now let's look at this diagram. This I got again from LangChain. It is encapsulating all the important topics related to memory, LangGraph. So this is the flow, okay. Node 1, node 2, and then we get an output. Initial state, final state. Now, checkpoints. When this state I was input to node 1, node 1 updated that state and we got a new checkpoint. Then again node 2 updated that state and we got a new checkpoint. So this checkpoint, as you can see, contains the state message, I heart LangGraph. The next, if I zoom in, you can also see the next node. You can also see ID over here and other metadata that it stores. And then thread, as you know, is a collection of checkpoints. It encapsulates all the checkpoints so that we can easily handle them during long conversations and enable memory. State snapshot. It is basically a data structure or a class. So every single checkpoint is a state snapshot object. Just like every message in LangChain is a human message or AI message object in the same way. And then these are some of the methods that we need to know about. So graph.getState basically provides us the current checkpoint, current most recent checkpoint. Graph.getStateHistory provides a list of all checkpoints, and graph.stream execute the graph from the current state. We'll look at this particular thing. Right now we will be talking about graph.getState basically. Okay, cool. Getting the current state of the graph from the thread. So no matter what, how many times you run your particular graph, when you use this method graph.getState, it will provide you the most recent or the current checkpoint being used in that graph. So if your graph is getting executed and in the intermediate step you want to know about the current checkpoint, you can use this as well. So there's the application for this. So state equals graph.getState configuration, and this will provide a state snapshot object to us. Okay, this is a pretty big one, so let's see if we can just but rather I fudged up, man. Blah, 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 blah. Where was I clicked, I cannot select all of this, I don't know why. Let me just go the old good old way, selecting everything. Let's take a look at this. As you know, each checkpoint is a super state, so this basically will contain all the states that the graph has seen up until now. Let's see, it's a pretty long one. Okay, you can see it over here. So first of all, the first human message, that is the first state, and then the second state, or I would say the updated state, or whatever, so it basically includes the entire conversation leading up to this point. Okay, if you don't understand this, if you don't understand this entire thing, you can just execute it yourself, do some hard work, brother, and you can understand this very easy. I believe in you, as I said. Okay, so this is an important method that we see how it works. It provides us the current state of the graph from the thread, or it provides us the current checkpoint. And as we know that each checkpoint is a super state of the previous one, so this particular, as this is the current checkpoint, it will be engulfing, or it will be a super state of all the previous states. So basically you can say that this current checkpoint includes the conversation history, the entire conversation history leading up to this point. Okay, now add messages reducer again. We know that whenever we are working through a graph with the messages state has the add messages reducer inbuilt. I've told you about this in the previous sessions. You can just take a look at them. We've seen that add messages reducer basically appends new states, or the new state which is being generated by a node to our original state. Basically this is the reducer that updates our state after each node, okay, in the backend. So we know that add messages reducer is used to update the messages key, but if you want to overwrite an existing message, we can use the message ID. So yeah, a very simple and very intuitive thing which I've talked about here. Let me just go somewhere else, man. Holy shoot. All right, I'm running out of space, man. So say that we have a message. Okay, say that we have a message. Let me zoom in a bit, which is something like messages, and then we have this human message, say I am fiddler. Okay, say that we have this particular message. Okay, and then we have another message which is messages, which is an AI message. Okay, hi fiddler. Okay, and if you put both of these, if I put both of these in the add messages reducer, okay, this is the function. You've seen how it works, but I'm just again revisiting everything so that I can tell you about the new functionality which I want to talk about over here. Then it basically provides me an output which looks like this messages, human message, this particular message, okay, this particular message appended, and on top of that it appends the other message which is AI message, hi Fiddler. Alright, so what that did is it basically appended this new message onto this message. So this is what add messages reducer has been doing for us. But now say that, okay, say that I have a particular message. Let me just copy it, and what I do is, just a second, let me go back. Fiddler, blah 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 blah. Fiddler here. Let me just go back. All right, yeah, cool. Okay, I was just checking if I'm in sync with everything that I have in the notebook. So messages, I'm Fiddler, and then I also include this particular ABC. Okay. So what I've done is I've also included this particular metadata about this message over here, which is message ID, that is used to uniquely identify a particular message. And now say that I have another messages which is of the same type, human whatever, AI message, Fiddler, hello. Okay, and this time, instead of directly putting both these messages through the add messages reducer, what I'm doing is I'm also including the message ID, and I am assigning the same message ID to this message as well. So now what's going to happen is, when I put these two through the add messages reducer, instead of appending these two messages, add messages reducer will understand that, okay, he has got this first message with this message ID ABC, and he has provided me another message with the message ID as ABC. It means that he wants me to overwrite the earlier message with the same message ID. So using this message ID metadata, we can actually overwrite stuff using the add messages reducer. So what it will generate basically over here is something like this. Okay, messages, AI message, Fiddler, hello, boom. Let me just zoom out a bit. Boom, boom. All right, cool. Fiddler, hello, and alongside that, I'll have, which is simply like, this is the content part, and there is the messages ID part. Message ID, okay, ID, or just the ID, whatever, ABC. So this time basically it got overwritten. So if this is very intuitive, right? If I tell you that, okay, add another message but the ID is going to be the same, it means that we will just overwrite it, because there cannot be two messages with the same ID, right? So why isn't it happening over here? Because here the add messages reducer knows that by default we append messages, and it will just create a new message ID for this by default, all right, now let's see it working. So first of all, this configuration, I'm updating it, okay, to run the code again from the start, and we have this code to run that code. Messages, this is the input, the configuration, the stream mode, and let's run it. So I've added -1 over here because I'm taking just the value section of the last state, and so this is the input. Hi Fiddler here, hello, it sounds like you're refreshing. Fiddler on the roof, how can I assist you today? Okay, now we're going to use this particular method called as graph.state to update the state. Now graph.update state is a method through which we can update the state without using a node. So this is basically the method that we're going to use to manually update a state, okay, at a checkpoint, whatever. So config messages contained, no, actually my name is Adolf Fiddler. Okay, so what I'm trying to do is I'm trying to use add messages reducer to append this new state. Okay, done. Now it tells us that okay, this has been appended at thread ID 5. Cool. Now let's see what is the new state. Graph that state, config values, get state. We are going to get the current state. Okay, good. So you can see we did not provide any messages ID, so this worked as normal. We updated the state with a new message and it appended it. So it looks like hi fiddler here, the AI message, and then the appended messages. Okay, now what we want to do is we want to overwrite the particular message by providing the same message ID. Now let's try a new message, a human message contain no, actually my name is Massey. Okay, and ID is this. I provided a message ID. By the way, how did I get this message ID? So this message ID needs to be new state dot, or I would say config values. So this message ID needs to be the ID of the message that I want to update. Okay, so this is going to be the message ID of this. Hi fiddler here, maybe this or this, whatever. All right, this. Okay, I want to update this state or override this state. So I provided the ID of this message. Now what I'm expecting is add messages reducer now will update this particular message instead of appending this message as a new message. Okay, config update state again, got updated. Now let's try to print it. Now see, instead of adding a new message to this particular checkpoint, what it did was it overwrote this particular message because we added message ID, matching message ID rather. So okay, we've completed the foundation that we needed to develop the human in the loop functionality. Now let's jump into that. All right, so we wanted to why is it not working, man? Holy shoot. Okay, all right, so we wanted to look into the approval technique of adding human in the loop. So interrupting the flow to allow the user to provide approval, we will use breakpoints concept to develop this feature in our graph. I'll add more. We will interrupt the flow to add human inputs. Okay, for this I've created a React graph as we have seen earlier in our sessions. So I've just created the multiplier, adder and divider tools, the simple tools, defined them, created a list out of them and binded them to the LLM. Now in this particular state everything is similar. I'm just trying to create the React graph using the tools condition and tool node pre-built options using LangGraph, and I'm also adding the memory functionality in it, so everything will be stored in the form of checkpoints in a thread. Now in order to add interrupt functionality, I would just write here, in order to add interrupt or breakpoint functionality, we need to configure it while compiling the graph. So we know that while compiling the graph we need to add the checkpointer feature, and alongside this checkpointer feature I am writing this new input parameter called as input interrupt before. So I am saying basically that this graph will have an interrupt before the tools node. So this is what it looks like. So it starts, goes to assistant, and then it has a conditional edge where it might go to tools and then back to assistant, or it directly goes to end, which is the function of a React graph. But according to my configuration, it will interrupt the graph before this tool step. So let's see how it works. Yeah. So we're planning to build this graph. Initial state to assistant node, which has the LLM in it. LLM binary with the tools, obviously. Then it goes to rules condition. If the LLM response has tool calls, it will go to tools node. If it does not have tool call, it will go to the end or output state. Okay. Now we have added an interrupt before tools node, right? Interrupt before tools node. Cool. Now let's provide an input to this. So messages, human messages, multiply 3 and 5. We have configured the thread, and then we are using graph.stream. Let's see what happens. You see, it provided us the tool call, but it did not go ahead with tools node and then back to assistant node to generate the response. Why? Because we had added an interrupt step before tools node. So right before it should have gone to the tools node using the tool call, it got interrupted. So now we are left with this tool call and multiply 3 and 5, which is the input query. So right now we are in this particular, all right, yeah, in this particular junction of the graph. Right, I will just do it like this. Okay, whatever this looks like, guys, come on. All right, right now we are here. We have the tool calls, but we cannot go to the tools node because we have an interrupt over here. So you can see the graph has executed till the assistance node and has stopped before the tools node as per the interruption provided by us while compiling it. Cool. So now at this particular junction, if we try to get the checkpoint of the graph, we get this. Values messages, multiply 3 and 5, and then the tool calls. Let me show you the tool calls. Yeah, this is the tool call section. The tool calls. Okay, so we just have this right now, and as I said, a checkpoint also stores the metadata, so it also stores the next node information, which you can access through this state.next. And we know that right after this particular checkpoint, we have the tools node, which hasn't got executed because of the interrupt. Now, what we want to do is, we want to know how can we execute this graph now. We have the interrupt feature over here and it's working fine. Now, how to continue the execution of the graph after this interrupt? Okay, then we will understand how can we add human input over here. So continuing the graph execution after interruption, one important thing, when we invoke the graph by providing none as input, it just continues execution from the last checkpoint, which is the tool call or assistant node's response over here. So one thing, okay, let me go back to graph.stream. Where is it? Yeah. So let me just go back to where I was. I mean, we can also show it over here. So right now we are over here. Okay, here. Now in this particular step, if I write graph.stream input equals to none, which is basically null in Python, and then the config, and then the stream mode, which is values over here. If we do not input anything, if we use none as the input, then it tells the graph to continue the execution, using the current state or checkpoint. When we started the execution, we provided a graph.stream and an initial state, because at that time, if we would have used none as the input, nothing would have happened, right? Because the current state was literally null. It wasn't anything. But right now, as we are at this particular point, we have a current state, we have a current checkpoint, which we saw using the getState method, right? This is the current state. So now if I want to execute the graph from here and not from here, I want to continue the execution, I will have to provide none as input, which will tell the graph.stream method that, okay, this guy is trying to continue the execution using the current state. It will just find the current state and take it as input, and the execution will get continued. Boom, 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 boom. Okay. So if you write the graph using none as input, it will continue from the current state and trigger the tools node and then go towards generating the final response. Let's see how it works. For eventing graph.stream, see that we have provided none as input, everything else stays the same, and we get the final output. So tool calls, multiply node triggered, 15, result of multiply 3 and 5 is 15. Now you might be thinking, why don't we have the human message, the initial human message over here, multiply 3 and 5? Why don't we have that? Because right now, the execution or the continuation of execution starts with this particular thing as the initial state, because we use the none as input. Okay. So basically, this is the method that we are going to use in order to continue the execution whenever we have an interrupt feature. So our graph runs and we encounter the interrupt feature. If we want to continue the execution, we will use this particular thing. Okay, now that we have all of this in our arsenal, we can see how can we incorporate human approval before executing the tools node. I want to say seek human approval before executing the tools node and moving ahead with the response generation. All right. So I've written a simple code over here. We have the initial state, which is multiply 3 and 5. I've configured a new thread because I want to start the conversation again. And for eventing graph.stream, initial state, running the graph until the first interruption, getting the user feedback now. Now once the graph gets interrupted, so once this runs, what's going to happen is graph gets interrupted before tools node. This is what's going to happen. Okay, let me just go here. Then I want to seek user feedback or user approval to move ahead with the execution. So I'll take the user input. Input should be proceed yay or nay. And if the user input is yay, I will continue the execution with the current state by using the none as input. And if the user's input is nay, I will use user denied graph execution. So let's run this. Maybe I need to run everything, man. I need to run everything. All right. I think I created this a few days ago. That's why it's generating this problem. Boom. Memory saver and then testing. Cool. Let me go there, back, and now execute it. So multiply 3 and 5, and it has generated tool call, but right now it has got interrupted over there. We are again at this particular point, and it is seeking an input from me. So say that if I say yay, it will continue and generate the response. It will call the tool node and then generate the final response. Well, what if I said nay? It should say user denied graph execution. Let's see that as well. We need to start a new conversation again. 5. Let's run it again. Again, we are interrupted at the tool calls before the tool node. Nay. Use it in LangGraph execution. So you might be thinking this is pretty simple. I mean, what's special in this, right? You might be thinking that this is pretty basic, but this is actually pretty revolutionary if you think about it. Earlier we were using the graph as a black box, everything was happening and we were just receiving the final response, but now we are actually prying into the intermediate steps using graph.stream, and we have added a human in the loop. Now without this human's feedback, this graph cannot produce the final response, which is pretty special. And now this particular execution, this particular code is pretty basic, but yes, it can be extended to infinite possibilities. We will see that when in the future. I want to actually upload a video when we are creating a proper agentic workflow which encapsulates all the features that we learn about. Okay, so this video was a little bit long than usual, but guys, you need to sacrifice a little bit of time to learn something, right? I know it sounds weird, but it is what it is. Okay, then in the next videos we will be continuing the human in the loop section. Where is it? This particular section, and we'll be looking at how to modify the states using human feedback, how to time travel, stuffs like that. Okay, see you later. Thanks for joining, thanks for learning, keep on learning, and yeah, bye bye.